My name is Aratz Manterola-Lasa, and I'm an engineer at WebStream, which was acquired last month by Confluent. So today I'm going to talk about a very common issue in Flink clusters, which is noisy neighbors. Basically, in other words, if you have ever encountered any kind of interference between one service or workload with your Flink cluster, this is the talk for you. I'm going to explain what it is, how is it currently solved, and how, using WebStream, which later I'm going to explain what it is exactly, you can get rid of it once and for all. So my talk's title is this one, which is too long, to be honest. I don't like it. I would have changed it. But basically, it mentions that if you have any kind of interference or resource congestions in your Flink clusters, together with a Kafka cluster, here you will learn how to erase it, get rid of it. So let's start with the most basic concepts. What are noisy neighbors? I was thinking about a real example that I could use as an analogy, and I came up with a very real example, but it's very simple and dumb, which is basically I live in a house and I have next door a couple of 60, 70 years old, and they are very lovely, and they walk their dog together. I say to them, hello, how are you? They smile at me, and these type of things. But one day, out of nowhere, they suddenly threw like a huge, crazy party. And I was like, what the hell has happened? And that's when I learned that I have many things still to learn from them. But the reason why I mentioned this example is that they were very calm, very chill. They were very nice, and out of a sudden, they become this nightmare, no? Like this crazy party monster. And noisy neighbors are something in those terms, in the sense that you can have a Kafka cluster, and there you can have multiple workloads reading and consuming and producing to it. For example, here in this diagram, you have a batch processor running batch analytics. Then you can also have Kafka cluster using like a communication hub between microservices. And then, of course, you have your Flink cluster. So a noisy neighbor is if one of these other workloads, let's say the batch processor, suddenly tries to consume a very, very big batch, and then it hogs or congests all the resources, or too many resources, in one of the Apache Kafka brokers, and then your Flink workload suddenly starts seeing like high spikes of latency or failures and retries. That's in the most simple manner explain what is a noisy neighbor. So how do we currently solve this issue? There are two main alternatives that people implement. The first one is by setting Kafka cluster quotas. Kafka cluster quotas is a mechanism so that you can limit how many resources each workload can consume. And if it exceeds, then this workload, and only this workload, will get throttled. Okay? This is implemented in Apache Kafka today, and you can set it. There are two main quotas that you can set. One is how many byte rate, like network throughput, each of the workloads can consume. And then the other one is the percentage of the CPU threads, Java threads, that it can use. But there is always a but. It's not ideal. There are three main reasons why. The first one is that the quotas are per broker. It's not like, oh, in my entire cluster, I'm going to have this quota set, and then this workload is never going to exceed this amount. No. It's per broker, and this means that you can very easily see that suddenly some broker is like throttling a lot one of the workloads, while all the others are not. In the end, how fine-grained your rate limiting is, it's not very good. And it means that you will end up over-provisioning and then underutilizing your brokers. The second and most important one, in my opinion, is that it's pretty complex to get it right. Like, if you try to set this up, the configuration is static. It's literally a file that you need to set and write. However, your workloads are usually dynamic. This means that, for example, it may not be constant rate. It may vary. It may be seasonal. And in that case, you need to manually also change the quotas. And at the same time, in order to set these quotas, for example, the byte rate, it must be also relative to all the other workloads that you have. So you need to have the big picture in advance, and once you have everything, you understand everything perfectly, then you can try to set the quotas. But I mean, in my opinion, this is like more an ideal world. OK, so the second alternative that you can try to do in order to get rid of the noisy neighbors is to mirror your Kafka cluster. Mirroring basically means just copying one of your Kafka cluster and doing like exact copy, in theory, into a secondary one. So this has the amazing benefit that it completely isolates one Kafka cluster from the other. In the diagram, you can see that you will have a Kafka cluster A with your batch processor and the microservices running and producing to it. But then in the second one, you have your Flink workload. So you can make sure that you will not suddenly get interferences with your batch processor. But again, there are a few buts. The first one is that it requires more infrastructure. You need to deploy more brokers, and obviously, also, you need to duplicate the data. This, in the end, translates into way more money. Then the second one is that, of course, if you mirror it, depending on how you configure the mirroring tool that you use, it means that it will end up having a higher latency. So in order to read from the second Kafka cluster, it may take a bit more. So if it's very, very low latency requirement in your workload, it's not really for you, I think. Then a very important concept here is that this is useful mainly for reads. If you mirror a Kafka cluster, you cannot really write into the same topic that you are mirroring, because otherwise the mirroring will like break. And then the last one is that, in theory, it's a copy of your original cluster. But in practice, it's not. The offsets, for example, are not preserved. So offset 1 in cluster A may not be the same as in cluster B. The data will be the exact same, and the ordering will be, but the offset's not. So there are some tools out there that you may be using, and you may not be aware right now, but they really rely in having offset preservation. So, OK, why not instead? And I think this is not a spoiler, but we use workstream. Now, I'm going to first start explaining what is workstream in order so that you can really reason why it's a very good solution in order to get rid of the noisy neighbors. So I'm going to go over what is workstream, then I'm going to explain the reasoning why we design it the way we design it. And then afterwards, after this, you will be able to understand, and I will explain how we can get rid of the noisy neighbors completely. And this time, once and for all. So the easiest way to understand what is workstream is by comparing against regular Apache Kafka. You can understand Apache Kafka as a bunch of brokers that they are using different resources like memory, CPU, and disk, with the ultimate goal of offering an abstraction of topic and partitions to the customers. And then usually, if this Apache Kafka cluster is serious enough or big enough, you will probably deploy in multiple availability zones to get durability and availability. And what will happen is that you will have, on the one side, the producers producing to one of the brokers. They will see what are the available brokers. They will find the leader one. They will send the data to the leader. And the leader will store the data locally and then send it to a bunch of followers in order to replicate it. Usually, like 3 times is the most common replication factor. And these followers will also store in their local disks. Note that in this flow that I described, there are 2 points where you get cross-AC availability zone networking. One is between the client, the producer, and the leader. They may not be in the same AC. They may be, or they may not be, depending on where the leader is suddenly selected. So in this case, you can end up having cross-AC networking. But then there is a second place where the leader and the followers, if you have a multiple AC deployment, they may also incur into cross-AC networking. Then, on the other hand, on the other side, you have the consumers consuming the data. And usually here, there is no issue with getting cross-AC networking, because there is this configuration called fetch from follower, where the consumers find the follower, or the leader, if they are lucky, in the same AC. And then they don't incur into this cost networking. The reason why I mention cross-AC is because clouds usually charge way more, and it's very expensive to do cross-AC, just for you to know. Now, workstream is exactly the same as Apache Kafka. It implements the same API, everything. But it does not have local disks at all. We literally get rid of them. Like, you can provision a server without local disks, and it will work. And instead, what we do is we use object storage, directly read and write. And don't confuse it with tier storage, because tier storage, what it does is it first writes into a local disk, and later offloads it to S3 or whatever object storage, and later it can load it back. OK, so now I'm just going to go over 3 more slides on why we get rid of the local disks, and then I'm going to jump into why this allows you to get rid of the noisy neighbors and interference between different workloads. The main one, and the first one, is the networking. As I said, the cross-ASC networking is very, very expensive. And in high-throughput workloads, this can be up to 80% or 90% of the costs of the TCO. So that's not all. Then we have also the retention. If you use cloud disks, like EBS, compared to S3, they are usually an order of magnitude more expensive to store their data. This means that even if the throughput is very low, if the retention is very high, then you can get a very high cost. It can go also up to 80% of your TCO. And then, lastly, is the operational cost. Once you get rid of the local disks, then your Kafka brokers, which, by the way, in workstream we call them agents to differentiate them easily, they become stateless. Stateless means that you can suddenly kill one of the nodes and nothing happens, because they don't have a state. They don't have zookeeper, kraft, they don't have a leader. Everyone is a leader. So now it's very, very easy to manage. Literally, you can just put an autoscaler in front of the agents based on the CPU usage, and it will work. You don't need to do anything else. OK, so here I have another high-level architecture diagram, but I'm going to skip it just for the sake of time. And then just let's jump into the most important part of this talk. How does workstream fix the noisy neighbors problem? So it does it with a feature that we call agent groups. Agent groups are basically a mechanism that we have to logically group agents and completely isolate these groups between them. This, maybe it's not clear to you yet why we can do this with workstream and why we can't with Apache Kafka. But the reason is that in workstream, there is no leader and there is no follower. So there is no need for replication. This means that, for example, in this diagram that you see here, we have an agent group in one VPC and then another group in another VPC, and they don't need any communication between them because there is no replication. The only thing that they need is the access to the object storage. So if both groups have the access to the same buckets in S3, for example, then they will be able to read and write the exact same data, but without any kind of interference between the servers, let's call it agents or brokers. And so the idea here would be that, for example, in the diagram, the initial diagrams where you have the batch processor, you would put it in one group, then you would take also the Flink cluster and put it in another group, and then you could take the microservices and put them in a third group. So, and it's very, very cheap, literally. Like, you don't need to provision more and duplicate the data. You don't need to provision extra brokers that are not really necessary, etc. So apart from the completely isolating the different groups, it has a few other benefits. The first one is that the data is consistent. There is no duplication of data, and the offsets are preserved. Like, all the groups will see the same data and the same offsets. The second one is that it's a single cluster. There is no need to connect the VPCs between them, for example, if you deploy, as I showed you in the previous diagram, in different VPCs, the different groups. And the last one is that, of course, there is no any complex configuration that you need to do. And lastly, that I forgot to add in these slides also, this works not just for reads, but also for writes. You can write in parallel for different groups into a same topic partition, and there will be no interference at all. They will simply create different files in S3. And lastly, if you also use workstream for this, you can very easily put an autoscaler in different groups, and you will get a very fine-grained deployment, where different groups can scale depending on their characteristics. OK. Then there are other things that may be important or interesting to explain. The first one is that there is a trade-off in order to use WarpStream. The main one is that the latency is a bit higher. The P99 of the producer is 400 milliseconds, 500 milliseconds. And then the end-to-end from producer to consumer is between 1 and 1.5 seconds. So this, obviously, it means that if you have very, very low latency requirements, it may not be useful for you. But if 1 second is good enough for your end-to-end latency, then you should try it out. However, we can also support different backends for different object storages. So for example, if you have an agent group that is used for low latency communications, you can, for example, use S3 Express one zone, that we support it, and then the latency can go way lower. For example, producer latency P99 would be 150, and then the end-to-end, I think it's between 400 and 600 milliseconds. I need to check it out, but I think it's more or less like that. And then, of course, there are other things that we take care of in order to support this, like we move from S3 Express the data and put it in regular S3 after some time, because it's cheaper to store it there, etc., etc. OK. So this was the main explanation. Maybe I see that I have enough time, so I will go back a bit to the high-level architecture that is also important to explain. This means that I've been talking faster than expected. Basically, here what I'm showing to you is the highest level diagram possible of WarpStream. And the architecture and design of WarpStream is bring your own cloud. This means that in your VPC, in customer's VPC, you will run the agent, which is the Kafka broker. And obviously, you will also store the data. All the data will be only on your VPC, on the object storage that you choose. And then, obviously, the producers and consumers. And then, in our side, in our backend, that we call control plane, we will store the metadata. You can think of the metadata as anything that is not the actual data, like the mapping of the files, the consumer groups, etc. Thanks to separating the metadata and the data, we are able to give you these agents that are fully stateless. Because if you would need to store the metadata in your local disk, then in the end, you would end up having a cheaper version of the Kafka brokers, but still stateful. And yes, this is the bring your own cloud design that we come up with. OK, so now I can go over the demo. The demo is very simple. Like it's very simple. It's just to show you how creating these agent groups is as simple as just setting a flag, and that's all, like literally. So in the demo, what I'm going to do is I'm going to deploy 2 agent groups. And in each of the groups, I will just have an agent running there. And then I'm going to show to you doing a metadata call to each of the groups that you can only see the agents deployed in that group. You cannot see all the others, so that they are fully isolated. And then I'm going to just produce and consume from each of the groups. I do it locally, and it's very simple. Just as a heads up, my terminal is the light theme, so don't be scared. OK, so here we have a WarpStream cluster. I just created it for this demo. And what I'm going to do, OK. It's a pre-recorded demo. They did not allow me to do it live. We are going to show first that we don't have any agents deployed. And then we are going to go to the terminal, and we are going to deploy a new agent. The command is very simple. It's just WarpStream agent. And then, after specifying that command, we are going to specify the agent group, which is the name of the group, the bucket URL, where usually is an S3 URL, but in this case, it will be just be a local file, the region of the cluster, and the cluster ID. Then there is also an agent key out there, which is for authentication, but it's not very interesting. So once we deploy it, we will run it, and we will refresh the console until we find that the agent is available. We can see there that we discovered the new agent with the group 1. It has an ID, the IP, and some other information that may be useful for you, like the version. OK, so now we are going to do the same, but for the second agent, where the difference will be that I will set the HTTP and Kafka port different because I'm running it locally, but if it's in another server, you don't need to. And then the agent group. We will set group 2. That will be everything that you need to do in order to run a secondary group. Then we're going to execute it again. And we're going to see, going to the console, that we can find this secondary group. After showing you this, what I'm going to do is I'm going to show you a script written in Golang, which, by the way, workstream is written everything in Golang. And this is script 2. And in the script, I'm going to create a Kafka client. I'm going to issue a metadata request. And I'm going to print all the brokers that I find in that cluster. OK? And so first, I'm going to do this by connecting to the agent that I deployed in the port 1992, which is from the group 1. So I'm going to execute this small script. And we're going to see that I can only find a single agent with the broker ID whatever, the address, and the port that we set into the group 1 agent. This means that basically if you connect to the group 1, you cannot find the group 2 agents. That's it. And now, just for the sake of proving that it's real, I do the same for the second group. You also find a second broker, but with a different ID and a different port. OK, so now the last steps are very, very simple. I mean, the first one is to just produce some record, connecting only to group 1, the 1992 port. And we're going to say, hello world from group 1. And then we are going to just show that in the console, we can see that this record is available. Again, this is a very simple demo. If I had a kid that I don't have, a child, I would probably be able to reproduce this. But the most important part is that you can, like, I'm trying to prove you how simple and easy it is. That's the main idea of this demo. So there you have, and you see that there was actually one record produced to that topic. And now we are going to do the same, but producing from the second group to the same topic partition. Okay? So yeah, we connect to the second agent, and we say, hello world from group 2. Amazing. And now we refresh, and voila. The second record. Now, lastly, what we are going to do is we're going to run consumers, first connecting to a group 1, and then to the group 2. This is basically proving that you can actually read and write the same data from any of the groups. And the only thing that you need to do is just point to this URL instead of this other one. Like, that's literally everything you need to do. And you see that you can read both of the messages, hello from group 1 and hello from group 2. And then we're going to do the second one. This is the last command that I ran in the demo. And we simply specify the agent from the second group. OK. And OK, perfect. We can see that we are reading the messages from the second group. OK. And this was all. This was my talk. Thank you very much for being here and listening to me. And if you have any questions, I have 6 minutes left if anyone in the audience has still something. Thank you. Yeah, we have a microphone for you.
Hi, first, good talk.
Thank you.
My question is how to ensure the offset between the two groups is on control plane with metadata.
Whether the offsets are in the metadata?
No, the offset. Where you ensure the offset is same on two groups.
like why the offsets are the same in both groups? Or?
Yeah.
The reason is because you literally are accessing the same data and the same metadata. When you mirror, what you do is you literally copy the data, but also the metadata into the secondary cluster, if you use like a mirror maker, for example. And this means that you may generate new offsets and will be like stored, these new offsets in the secondary cluster. In our case, there is only one cluster and one source of truth, which is our metadata backend. I don't know if I'm explaining or if I'm answering your question.
Yeah.
Yep.
Is that. Thanks.
OK. Thank you.
Thanks for the interesting talk. I was wondering, like, when the data is actually written to object storages like S3 or similar, does RobStream use or make use of locking mechanism in there? So, like, I was wondering if you were using like a fused data system mounted on some machines, so you can maybe reduce latency and use eventually consistent mirroring to the object storage. Is that possible, or do you need, like, I don't know, is WarpStream using these locks in order to make sure that data isn't written by two agents at the same time?
I'm not sure I fully understand your question. I'm sorry. Could you maybe... So can you explain me a very concrete example on what could go wrong, or what are?
So let's assume we have two agents running on two different machines, and now they, I don't know, for some reason try to write at the same object inside object storage. So that could be prevented by a lock, right? So.
Okay. Okay, I see. Okay, good question. No, so what happens is that different agents will generate completely different files with random UUIDs, or well, are not UUIDs, but let's say are random UUIDs. And then, once they create the file, they go to a metadata store and they say, hey, I have this data, please. Commit it into a metadata store and assign some offsets to this data that is already flashed to S3. So the flow is basically they just generate random files, they go to the metadata store, they assign offsets to these files, and they return these offsets to the client.
OK, I see. Thank you.
Yeah, so there is no possibility to collapse between them.
And that's probably also the reason why the latency is so much higher than using regular Kafka, right?
Yeah, because the object storage latency is pretty high. Yeah.
OK, yeah.
We also actually batch in the agent. So in order to reduce costs on object storage, because the cost of object storage people don't know, but the cost model is based on the amount of puts that you do. So in order to reduce, OK, you know it. So in order to reduce the amount of puts, we buffer either based on time, like 250 milliseconds, but you can tune it if you want, or otherwise based on size. So if you reach some amount of file size or like data buffered, you just flash it to S3.
I see. OK, thanks.
Thank you.
Thanks for the talk. So I would assume that you're still producing a lot of small files, right? Are you having any mechanisms to consolidate files into bigger ones?
A lot of small files. With the buffering, not really. We don't generate that much. But it's true that we have a mechanism on the background, which is the compaction jobs that take multiple files. Maybe that's what you were referring to.
Yeah, I guess, I mean, you'll need something like that, but it's like especially for trickle use cases where you like have not high throughput.
OK.
Right, then the size of the files will be just tiny, and you're paying for the put cost for every single file and for the get cost of every single file.
That's a very good question. Actually, somebody in the conference asked me that. For very, very low throughput workloads where using object storage may be a bit too expensive, although in theory it's probably less expensive than using local disk or whatever. But what we are going to offer, I don't know if very, very soon, is having a DynamoDB-backed object storage. This means that the DynamoDB cost model is not based on the amount of puts, but on the amount of data. So this will be more cost-effective for these use cases. Yeah. Thank you. Thank you very much.